right, here we go. 6.4, integration by use substitution and pattern recognition. Now, depending on whether you have to take this in college and what your professor believes. Some professors make you use use substitution every time. Other people just let you use pattern recognition or whatever method you can do. But basically, what we're going to be doing today, we have that power rule, right, for integration, where you add 1, divide by the new power. We don't have any product, quotient, or chain rules. So what this pattern recognition and integration by use substitution is recognizing that chain rule in reverse. Okay, so just as a review, we can take this derivative. So the derivative of tangent would be secant squared, okay, of e to the 4x squared times the derivative of the inside, which would be e to the 4x squared times 8x. All right, so that's something that we're really good at. You could take the derivative, no problem. Now, if we didn't just do this, you might not be able to complete the next example. But the next example, okay, evaluate the integral of this. Now look, this matches piece by piece exactly what we have. So we are able to evaluate that as tangent of e to the 4x squared, okay, plus c. So these are going to be where we recognize that parts of these are the derivative of some other function, okay? And usually we're going to look for like the most complicated package of functions, okay? And then we'll look for pieces that might be derivatives of that inside package, all right? And this is something that you can read, okay? So let's see. In general here, here's the symbolic representation of this. All right, so I know it's kind of confusing, but if you think about it this way, maybe. All right, if you take the derivative, the integral of something like this, okay, where you recognize that part of it, this part, is the derivative of the inside function, then it's just going to be that the antiderivative of the f function, okay, so f, with that g function still inside, okay, plus c. So it'll help when we have practice, okay? But you're looking here where you have the product of two terms. That's what we're looking for. And one of the products is the derivative of the other. Maybe that's a better way of explaining it. Okay, so you have two things being multiplied, and one is the derivative of the inside of the other. So let's take a look. Here we go. Alright, so there is the official thing, antidifferentiation of the composition of a function. Alright, and U-substitution, this is something where you can read. I'd rather just show you an example for right now. And we will do both ways, and you decide which one's easier. Alright, the first way that I'm going to do it is U-substitution. Okay, so you have this inside function. And if I take the derivative of that, this is what you're thinking. You don't have to write it. If I take the derivative of this, that's just 2x. So look, I have that there. All right, so if we let u equals x squared plus 1, then du would equal 2x dx. Okay, so now I can rewrite my integral, because instead of writing 2x dx, I could just write du. And instead of writing x squared plus 1 quantity squared, I could just write u squared. So now my integral changed from u to u squared du, and that's something that's really easy to take the antiderivative of. That would be using that power rule, 1/3 times u cubed, okay, plus c. But instead of writing u now, the last thing that you go back and do is replace what you originally let u be. So there you go. The other way is pattern recognition. All right, let me change the color so it's a separate thought. Okay, how you do this is you notice that 2x is the derivative of this inside function. Okay, and so that inside function, that's something, the integral of something squared. All right, I'll just rewrite it again. So we have that's the derivative of this inside function And that inside function is just something squared. So now you just use the power rule. So add 1 to the power, divide by the new power, and you get x squared plus 1. And don't forget your plus c. All right, and sometimes, if you're just beginning, you might want to check it. This isn't something you have to do. But let's take the derivative of this. 1/3 times x squared plus 1 cubed plus c. All right, use the power rule here. 3 times 1/3, that's just 1, times x squared plus 1 squared times the derivative of the inside. All right, and the plus c, the derivative of that, 0. That's exactly what we started with. So right now, some of you may want to stick with the U-substitution, but if you can do pattern recognition, you're going to be able to do this a lot faster. All right, so we'll have a lot to practice that. All right, so this time I'm going to start with the pattern recognition. All right, so again, we notice this, the derivative of x squared plus 1. If we do that, it's 2x. So we have 3x here. So we're only off by a constant, so that's not so bad. But I don't like that constant being there. I'm going to just pull it out for a second. All right, so if only that was a 2x there, and I kind of can make it a 2x, and so we're going to see this later on. If I multiply this inside by 2, I can just multiply also by 1/2, and I would just bring that in the front. Okay, because if I multiply by 1/2 and multiply by 2, they cancel each other out. So it's kind of like we made it what we wanted it to be. We had to correct it, okay, because it wasn't originally there. All right, so now instead of where the last time it was x squared plus 1 quantity squared, now it's sine of that. So we can kind of think about ignoring this. This is the derivative of that inside function. I'm going to pull my constants there. The antiderivative of sine of something is negative cosine of that something. Okay, plus c. And now if you want to just rewrite it, you could rewrite it as negative 3/2 cosine of x squared plus 1 plus c. Okay, and again, the other way I'm going to show you, you don't have to use it, but you can. Maybe you'll like this way. We're going to let u equal that inside part. One more. Okay, x squared plus 1. The derivative of that would be 2x dx. And I don't have a 2x dx, and I'm going to pull this 3 out so I could show you what I'm doing. Okay, x times sine x squared plus 1 dx. So I don't have a 2x dx, so I'm going to pull that 2 over here. 1/2 du equals x dx. Now I have this. I let u equal this part, so there aren't any x's left. So now I can rewrite this as 3 times. Now instead of putting this, actually for the first time I'm going to write it right inside. I'll show you, okay? Instead of writing x dx, I'm going to write 1/2 du. Instead of writing sine of x squared plus 1, I'm just going to write sine of u. Now I don't like that constant in there, so I'm going to pull it out. Now we're just integrating sine of u du. All right, so the antiderivative of sine, I'll pull my constant down, is negative cosine, okay, plus c. And now for my last step, instead of writing u, I'm going to write what my u was, x squared plus 1. So we get the same answer, it's just a different method. Some people can think about it a little bit faster. That's this red version. Some people like to see it laid out. Okay, later we'll get to some where you have to use U-substitution, but when you don't, it may be quicker to use the other method. All right, so maybe we'll just do 1 or 2 other problems, not too many, because I want to talk about these tomorrow or in class. All right, so when you integrate by pattern recognition rather than U-substitution, the multiples are going to be the only thing that throw you off, the constant multiples. All right, sometimes there's a constant multiple, like that 3 in the last problem, where you could just pull it right out. Okay, other times you have to have what's called the correction. All right, so you have to correct, you wanted it to be 2x, so in order to be 2x up here, you have to multiply by 1/2 to correct it. And the only other kind would be something that comes from the power rule. Like if you have u to the 1/2, if you integrate that, you're going to get 2/3, so like a constant like that. All right, so, and you never want to forget your plus c. So we'll do this problem here. First, before I do anything, I'm going to pull that 1/pi out. It's a constant, okay? It's just a rider. It comes along for the ride. Okay, now, using pattern recognition. This is something you don't have to write, but it's something that I'm thinking about as I'm doing this problem. The derivative of x squared plus 1 is 2x. Okay, so I'm very close to that. So if this was 2x, this would be a great easy problem. It's not. So I have to correct it. All right, let me go back to my purple here. So I'm going to have this 1/pi. I have this 1/2 as that multiple correction there. Okay, and then, oh, why did I do that? Now it's just dealing with the power rule. Okay, so it's add 1 to the power, divide by the new power, and then I'll just write what's on the inside there. And then I don't want to forget plus c. And if you feel like it, you can put this all together, 1/6 pi times x squared plus 1 cubed plus c. All right, so it's not so bad. And again, I'll show you the U-substitution. You do not have to use it, but if you like it, all right, we would let u equal the inside function. We'd let du equal, the derivative of that would be this. This is where that correction comes in. All right, so I'm going to just rewrite this now. I'm going to pull that 1/pi out to the front again. Instead of writing x or dx, I'm going to write 1/2 du. I'm going to pull that 1/2 out. All right, and then instead of writing x squared plus 1 quantity squared, I'm going to write u squared du. Okay, add 1 to the power. I'll put that there. So I'm going to add 1 to the power, divide by the new power, and instead of writing u, now I just fill it back in with x squared plus 1. So we get 1/6 pi x squared plus 1 cubed plus c. All right, so that's a pretty good set of problems there. You could do a couple on your worksheet now if you'd like to try. Some of them you're not going to be ready for, all right, but some of you are. Just take a look, and we'll pick a couple in class. All right, have a great day.